Hi, welcome to a new session of electrical machines. In today's class 5, we are going to continue with single phase transformer on load, the basic problems and solutions. So what we have learned from our previous class, that is class 4 under single phase transformer, the voltage equation of the primary is given by V1 is equal to minus E1 plus I1 multiplied with the impedance value, that is R1 plus JX1, which is given by equation 1 and 1a. This is a small modification, and the induced voltage in the secondary is given by V2 plus I2 multiplied with the impedance Z2. So these two equations are the main equations, and also we have seen in our class 4 that when the resistor load, inductor load and capacitor load are connected, the behavior of the transformer, the relationship between voltage and current and their phasor diagrams are represented by these waveforms. Now we are going to see when the transformer is having a small no load current. So we are going to trade the angle, that is a phase angle phi 1 between the input voltage and input current, which gives the power factor angle of the transformer. And the no load current, when it is considered, therefore the voltage drop associated with the no load current will be in the terms of I1 R1 and I2 R2 for the real component values, and the reactance drops will be I1 X1 and I2 X2, which are compared to I1 R1 I2 R2 are very small. So if at all we neglect these values, and the total flux, or we call it as the main flux of the transformer is maintained as constant, so that we are treating as phi. If that is true, then from the actual transformer conditions, we can deduce the relationship between voltage and current for the load conditions. For pure resistor, it will be E2 is equal to V2 plus I2 R2, neglecting the reactance drop here, and we are treating this equation as 3. And the input voltage, which is given by V1, is equal to E1 plus I1 R1, and that we are going to treat as equation 4. Now this is for pure resistive load, but in practical we don't have a pure resistive load. Always the load is associated with the reactance component. So if for the RL load, the E2 value will be equal to under root of, we are trying to get the magnitude value, so that is V2 plus I2 R2 cos phi plus I2 X2 sin phi whole square plus I2 X2 cos phi minus I2 R2 sin phi whole square. So the real component and the imaginary component are separated and the magnitude is estimated, and when the drop is neglected, E2 will be equivalent to V2 plus I2 R2 cos phi plus I2 X2 sin phi. And similarly, the input voltage V1 will be equivalent to E1 plus I1 R1 cos phi plus I1 X1 sin phi. So these two equations we are going to treat as equation 5, equation 6. You have to keep in your mind that for RL load, E2 in terms of V2 and the drops will be in positive notations. Similarly, the input voltage V1 is equal to E1 plus drops will be on positive notations. Now, what if we have RC load? For RC load, the E2 will be equivalent to E2 is equal to V2 plus I2 R2 cos phi minus I2 X2 sin phi. Now, the input voltage will be in terms of E1 plus I1 R1 cos phi minus I1 X1 sin phi. So this is how equation 5 and 6 are different from equation 7 and 8. So depending upon lead or lag conditions, we have the voltage and current relations, which are given by equation 5, 6, 7 and 8. So let us go with the first problem, where you have a 230 by 460 volts transformer has a primary resistance of this value 0.2 ohms and reactance as 0.5 ohms, and the secondary resistance and reactance values are 0.75 and 1.8 ohms. We need to calculate the secondary terminal voltage when the supplying load current is 10 amperes at 0.8 power factor lagging. So for this, we are going to take the data which is given to us. So you can see here V1 by V2 is taken as 230 by 460 volts. The primary drop, secondary drop, resistor and reactance values are given in ohms, and the load current is 10 amperes, that we are going to treat as I2, and the power factor is 0.8. Therefore, the power factor value is given as 0.8, which is given by cos phi. Now, from the transformer ratio, we know that V2 by V1, which is equivalent to K, which is equivalent to 2, because here 460 by 230 is 2. Now, in terms of current conditions, I1 is equal to K I2 from transformer equation. So the I1 value will be equal to 20 amperes. So it is nothing but the double the load current. Now with that, we are going to apply the values and we are going to substitute in the equation for V1, and from that we are going to get the value of E1, which is equivalent to 220.8 volts. So actual transformer, the induced primary voltage is obtained to be 220.8 volts. Now again, from the transformer ratio, E2 is equal to KE1. With that, we are going to get the value of E2 equal to 441.6 volts. Now once E2 is obtained, we can get the value of terminal voltage, which is our requirement, which is equivalent to E2 minus I2 R2 cos phi minus I2 X2 sin phi. Substituting the above values, we are going to get the value of terminal voltage, which is nothing but 424.8 volts. Now this is a result for lagging power factor. Now you can see another numerical where we have 220 by 440 volts transformer with primary and secondary real and reactive values. We need to calculate the terminal voltage. Here the load current is 12 amperes and 0.8 power factor is leading. For that, after collecting the data from the question, we are getting the value of K, which is same, that is 2, fortunately, because 420 by 220 is 2. Now we are calculating the primary current, which is 24 amperes. With that, we are going to estimate the value of E1, which is nothing but equivalent to 223.696 volts. Now once E1 is obtained, we can get the value of E2, which is 447.4 volts. Now once E2 is obtained, we can easily get the value of V2, which is 454.3 volts. Now you can make a chart or you can make a column, and based upon the input and output terminals of real and reactive components, you can estimate the voltage and current relations. And similarly, I have framed a question 3 and question 4, for which the terminal voltages are obtained to be 419.7 volts and 470.4 volts. You please do the calculations from your side and check whether you got the same values or not, and comment in the chat box whether you are able to understand the actual concept of the single phase transformer when it is practically loaded. So that's all for today's class. I hope you like this video. Please share among your friends, subscribe to this channel and press the bell icon for your future notifications.